So hello all. So today let's discuss something interesting, which is the basic of all chapters, I would say. So that's about carbohydrate chemistry. Okay. So before moving on, I need your idea on carbohydrate. What do you think a carbohydrate means? So the definition of carbohydrate. So a carbohydrate is nothing but either an aldehyde or a keto derivative of polyhydroxy alcohol. So let me just write it away. So it's called as an aldehyde or keto derivative of polyhydroxy alcohol. Okay. So what do you mean by a polyhydroxy alcohol? It is derived from this polyhydroxy alcohol, I said. So let me give you an example. So one of the commonly or simplest alcohol of reference is our glycerol. Okay. So what is the structure of glycerol? Can anyone say me? I hope you all know. So it looks something like this: CH2OH, CHOH, and then we have another CH2OH, right? So this is our polyhydroxy alcohol because we have many hydroxyl groups. So that is why it is called as polyhydroxy alcohol. So this is our glycerol. So it should be either an aldehyde derivative or keto derivative. Okay. So let me draw an aldehyde derivative of this glycerol. Okay. So this becomes so what is the functional group of an aldehyde? It's nothing but C double bond O and H. So CHO is a functional group, right? So this is how it looks: C double bond O and H. So this first carbon unit is changed this way, and then we have CHOH, and then we have CH2OH. So what is this? So this is nothing but your, so imagine this is glycerol. This is an aldehyde derivative of glycerol. So this is called as glyceraldehyde. Okay. And what about a keto derivative of this thing? Okay, let me try to draw a keto derivative. A keto derivative, what is the functional group of ketone? Nothing but C double bond O, right? Okay, so now let me draw the keto derivative. It looks something like this: CH2OH, and here it is our functional group, C double bond O, and then we have sorry, and then we have CH2OH. Okay, so we have our functional group here. So this is a keto derivative of glycerol. So what is this called? This is called by a special name called dihydroxyacetone. Okay, this is called as dihydroxyacetone. Okay, so this is in short about what carbohydrate means. Now let's talk about the different types of, or the classification of carbohydrates. So carbohydrates are classified based on the number of sugar units it contains. Okay, so if it contains a single sugar unit, it might be either a glyceraldehyde or to say either of these sugar components. So if it contains only one single sugar unit, it is called as, you all know it by the famous terminology, which is monosaccharide. Okay, so if it contains two sugar units, it ultimately is called as disaccharide. Three sugar units, it is a trisaccharide. So up to say for example 3 to 10 sugar units it contains. So what is it called? It's called as an oligosaccharide. And if it contains more than 10 sugar units, it is called as a polysaccharide. Okay, so a polysaccharide is, one second. Okay, so a polysaccharide is something which contains more than 10 sugar units. Okay, 3 to 10 sugar units is called as oligosaccharide. So oligosaccharide is a terminology used when it contains 3 to 10 sugar units. Fine. So this is about the classification of carbohydrates. So we began with what a carbohydrate is, and we looked at glyceraldehyde and how we looked at glycerol and how glyceraldehyde and dihydroxyacetone are derived from glycerol. And moving on, we saw the classification of carbohydrates. We saw what a monosaccharide is, what disaccharide is. We saw what oligosaccharides are, and we saw what polysaccharides are. So moving on to the common monosaccharides. Now we'll discuss about the monosaccharides. So monosaccharides are further classified based upon the number of carbon atoms that it contains. Okay, so we saw in glyceraldehyde how many carbon molecules were there, carbon atoms were there. So we had 1, 2 and 3, right? So that's called a triose. Okay, so in triose we have an aldo group and we also have a keto group. So the aldo triose is nothing but a glyceraldehyde, and the keto triose, as we already saw, it is nothing but a dihydroxyacetone. Okay, so this is with regard to trioses. Now let's move on to tetrose, which means there are 4 carbon units here. So the aldo derivative is called as erythrose, and the keto derivative you just have to add ulose, okay, to a suffix called ulose to it. So it's called as erythrulose. Okay, and pentose is when we have 5 carbon groups, and the examples being arabinose, xylose and ribose. So you just have to keep adding the suffix ulose to it. Okay, arabinose does not have a keto derivative, whereas xylose, the keto derivative is xylulose, and for ribose the keto derivative is ribulose. Okay, so moving on to hexose, which is the most commonest, the most we are most fond of hexose, right? Because what all aldehyde derivatives do we have under this? We have glucose, the most famous one, and then we have galactose and mannose, and the keto derivative is fructose. Okay, so this one we know. And heptose is when there are 7 carbon moieties and we do not have an aldo derivative. The keto derivative is called as pseudoheptadose. Okay, so this is in short about what a carbohydrate is, the classification of carbohydrates, and then the classification of monosaccharides. Okay, so moving on to disaccharides. So what do you mean by a disaccharide? So a disaccharide simply means 2 monosaccharide units combining together. Okay, so the 2 monosaccharide units, they combine together by, there should be a bond between them, right? And that bond is called as glycosidic bond. Okay, so a disaccharide is simply nothing but a monosaccharide plus another monosaccharide, and the bond here is glycosidic bond. Okay, so this is about disaccharide. And under disaccharides we do have a classification. So we can classify disaccharides into, okay, so disaccharides can be classified into reducing disaccharides and the non-reducing ones. Okay, so we have reducing disaccharides and non-reducing ones. So what are the examples under reducing disaccharides? So we have maltose, we have isomaltose, and then we have what else do we know of? Lactose and lactulose. So these are the examples under reducing disaccharides. Under non-reducing disaccharides we have 2, that is sucrose and trehalose. Okay, so now let's see why certain molecules, certain disaccharides are known to be reducing and why certain are classified in a non-reducing category. Fine, so let's move on to maltose. Before that, we have talked extensively about what a carbohydrate is and how carbohydrates are classified, and then we moved on to the different classifications of monosaccharides, right? And I told you, like, we are most bothered about something called glucose. So we have to first decipher the structure of glucose. So glucose is a, what type of sugar it is? It is a hexose, right? So hexose means it contains 6 carbon atoms in it. So what is and is it an aldehyde or a keto derivative? It is an aldehyde. So basically it should have a functional group which is CHO, and it is a hexose, meaning it should have 6 carbons, right? So now let us draw the 6 carbons. 1, 2, okay, 1, 2, 3, 4, 5 and 6. Okay, so the first thing is we have the keto group, which is a functional group. So let me draw the functional group here. Okay, and then C2 onwards, how is it written? So it is written something like this: CHOH, and then we have COH, and then we have CHOH, then we have CHOH, then we have CH2OH. Okay, so this is how a glucose molecule looks like. Okay, so we have CHO, which is a functional group that is in the that is in the first that occupies the first carbon, and then in the second carbon the H is oriented on the left side and OH is on the right side, and then just remember that at third carbon the OH is on left side. Okay, otherwise the OH is always on the right side. This is how a glucose molecule looks like. Okay, so now let's see okay, maltose. Okay, so we have okay, so now we'll look at each of these. So under reducing, I told you we have maltose, sorry, under reducing we have maltose, we have isomaltose, lactose and lactulose. Let's talk about each of these. Let's begin with maltose. Okay, so maltose is a disaccharide, meaning it is made up of two sugar units, right? So what are the two sugar units? Let me draw maltose here. So maltose is a combination of glucose plus another glucose in what is called an alpha 1,4 glycosidic linkage. Okay, so alpha 1,4 glycosidic linkage. So let me draw two glucose molecules and next let me draw this glycosidic linkage. Okay, so how do you draw glucose? It is C double bond OH, CHOH. Okay, so it is COH H, and then we have CHOH, then we have CHOH, and then ultimately we have CH2OH. Now let me draw another glucose here, which is C double bond OH, let me draw it parallelly. So CHOH, COH H, CHOH, CHOH, and then CH2OH. Okay, so now the bond is alpha 1,4 glycosidic linkage, which means this first carbon, okay, and the fourth carbon here, 1, 2, 3, 4. So this fourth carbon, these two, between these two carbons, okay, so between these two carbon there is a glycosidic bond. So this is the structure of maltose. Okay, so maltose is nothing but a combination of glucose plus glucose. It's a disaccharide, meaning it is made up of two sugar units. So one of both the sugar units here are glucose units, and they are linked by alpha 1,4 glycosidic linkage. Okay, and this is considered a reducing sugar because although in the first glucose moiety the functional group is involved in this glycosidic bond formation, in the second glucose moiety if you see the functional group is free, right? Since it is free, it is considered to be a reducing sugar. Okay, so that is it. If this is also occupied by a bond, then it is considered non-reducing. But since here it is free, it is considered a reducing sugar. So this is about maltose. Now let's talk about the next thing, which is, what was the next thing? It was isomaltose, right? So isomaltose, okay, so this isomaltose is also a disaccharide. So this is nothing but again glucose plus glucose, just like maltose, but here the bond involved is alpha 1,6 glycosidic linkage. Okay, alpha 1,6 glycosidic linkage. Now I'm not going to draw this, maybe we'll just revise this bond here. So it is alpha 1,6, okay, sorry. So this is alpha 1,6 glycosidic linkage. So which means which two units should be linked? The first carbon here and the sixth carbon, 1, 2, 3, 4, 5 and 6. So this is a sixth carbon. So these two are involved. Again, is this reducing or non-reducing? It is reducing because this functional group is free. Okay, so this is about maltose and isomaltose. Now let's look about the next thing here, which is okay, so next thing here, which is lactose. Okay, so lactose, it is a combination of, it's a disaccharide, so it's a combination of galactose plus glucose. Okay, and the bond involved is beta 1,4 glycosidic bond. Okay, so this is it. So now, having said this, now we'll have to draw galactose. So galactose, for time being, you just remember galactose looks something like this. Okay, okay, So we have CHO, it is similar to glucose. So galactose is a C4 epimer of glucose. Okay, so this is C1, C2, CHOH, C3. Here it is OH and H, C4. So C4 in glucose it was like this, right? In C4, C4 of glucose, H was on the left side and OH was on the right side. So this is in reverse. So you'll have to draw OH here and H here. Okay, and C5 we'll have to follow the same thing, which is H here and OH here, and then finally we have CH2OH. So this is nothing but your galactose. Okay, remember this is not glucose, this is galactose. Okay, and now let's draw. So we are done with galactose. Now the simple one, there is glucose, which is easy. C double bond OH, and then we have CHOH, and then we have COH, and then we have CHOH, and then we have CHOH, and finally CH2OH. So what is this? This is nothing but your glucose. Fine, and the bond involved is beta 1,4 glycosidic bond. So beta 1,4, 1,4 means the first carbon here and the fourth carbon. So let me number them, 1, 2, 3, 4. So the fourth carbon. Okay, so these both are involved in bond, and again, is this reducing or non-reducing? It is reducing because CHO, this functional group, is free. Okay, so this is about lactose, and lactulose is nothing but, here lactulose is in some way different. Just remember, lactulose is a combination of galactose and fructose. Okay, so this is not lactose was a combination of, lactose simply is a combination of galactose and glucose, but lactulose, you can see there is a prefix ULOSC. So whenever you see the prefix ulose, it means that it's a keto derivative, right? So since it's a disaccharide, one of the sugar units should be a ketone, so it is the second one, just fructose here. Okay, lactose was galactose plus glucose, lactulose is nothing but galactose plus fructose. Fine. Okay, so now let's move on to, now we are done with all the reducing sugars. Now let's discuss sucrose plus trehalose. Okay, so now let me draw sucrose. Okay, so sucrose is a combination of glucose plus fructose. Okay, and the bond here is alpha 1 beta 2 glycosidic bond. Okay, so now let me draw glucose and fructose. So glucose, we all know the formula, C double bond O and H. Okay, and then we have CHOH, COHH, then we have CHOH, then we have CHOH, and then we have CH2OH. So this is nothing but a glucose. Okay, so fructose, I'll simply draw it this way. We have so fructose is also a hexose. I'll draw 6 carbons. Okay, so at which carbon atom is a functional group present? It is present in the second carbon. So second carbon has a functional group. Okay, I'm just drawing it in a simple way. So now I told you the bond here is alpha 1, the bond here is alpha 1 beta 2 glycosidic bond. So alpha 1 means this group here is involved in bond. This is bonded to the beta 2 carbon. So beta 2 carbon here is C double bond O, okay, the second carbon. So these two are involved in glycosidic bond. If these two are involved in glycosidic bond, is there a free functional group in any of the two units? No. The functional group here is also involved in a bond, and the functional group here is also involved in a bond. So both these functional groups are not available freely, and hence is it reducing or non-reducing? It is non-reducing. Okay, so this is it. Now let's see the next one here. So we saw So we saw sucrose also. The other one remaining here is trehalose. So we'll see trehalose. Okay, so trehalose is nothing but it's a combination of glucose plus glucose. Okay, so both the glucose are involved in bond, but here the which of the carbon units are involved? It's the first carbon of both the glucose units. Okay, so let me draw that. So trehalose is nothing but glucose plus glucose. The bond here is alpha 1 comma 1 linkage, glycosidic linkage. So now let me draw trehalose, glucose plus glucose. I'll simply draw the schematic, okay, for the, this is C1, C2, C3, C4, C5 and C6, and we have another glucose, so C1, C2, C3, C4, C5 and C6. So it is alpha 1 comma 1 linkage, which means this is the first carbon which is involved in a glycosidic bond with the second carbon here. So in this also both the functional groups are involved in bonds. So there is no free functional group, and hence do you think it's reducing or non-reducing? It is non-reducing again. Okay, it is non-reducing. So this is about our glucose, disaccharides. Okay, so now let's move on to ring structure. So far whatever I drew, whatever I showed you is called as the Fisher's projection. Okay, the linear projection, which is otherwise called as the linear projection, is otherwise called as Fisher's projection. Okay, but later in the year, to be, I'm not very sure, in the year 1965 I presume, a scientist called Haworth, he found that in solution most of the glucose and fructose, they exist in ring structures. Okay, they do not exist in this extended linear form, but rather they are present in something called as ring structures. Okay, so there is a ring structure for glucose and there is a ring structure for fructose. So let's see the ring structure for glucose. Okay, so in glucose, let me show you a glucose which was drawn here. Okay, so this is our glucose which was initially drawn. So this is a linear what to say, a Fisher's projection. So this ring projection or ring conformation occurs when this first carbon, it is hydrogen bonded or it is interacting with this fifth carbon. Okay, so this first carbon and the fifth carbon, so intramolecular interaction happens. Okay, so intramolecular hydrogen bonding happens between the first and the fifth carbon, resulting in a six-membered ring structure. Okay, so this six-membered ring structure is called as hemiacetal form. Okay, so this is okay, this is it. So let me draw this. The ring structure for glucose looks something like this. For glucose, it looks something like this. So we have a, so this is the first carbon, the second carbon, third carbon, fourth carbon, and then fifth carbon, and sixth carbon is attached here. Okay, so this is nothing but the six-membered pyranose ring of glucose. Okay, so glucose ring structure is six-membered. It is called as pyranose ring. Right. So similarly for fructose, so I told you, I discussed you the structure of fructose. In the structure of fructose, as we drew here, yeah, this one here. Okay, so we can see that the functional group is in second position. So this functional group, this C2, is going to be interacting with C5. Okay, again there is intramolecular hydrogen bonding that is going to cause the ring structure. So the linear straight chain. So remember, there's something like this. Let me show you. There's something like this. This is a straight chain. Okay, this is a straight chain, but because of interaction, this first carbon, it is going to interact here with your fifth carbon or so. So what happens? There is a ring that is formed, right? So this is how the rings eventually form. So here it is C2 that is involved in ring. So here what you get in fructose, we get something called as furanose ring, and this ring is five-membered. Okay, so this ring is 5-membered. So this ring of fructose looks something like this. Okay, so we have this C2 is here. No, C2, yeah, C2, C3, C4 and C5. C6 is present here. Okay, so this is how the ring structure of, this is ultimately your furanose ring, which is a 5-membered ring. Okay, so we can see this is 5-membered, whereas this is 6-membered. This is pyranose ring and this one is furanose ring. Okay, so this is about other ring structure. Now let's look at oxidation and reduction. See, basically I told you these are aldehyde and keto derivatives of polyhydroxy alcohol. So basically what we are now looking at is an aldehyde. Okay, so this aldehyde, if it gets oxidized, it results in the formation of an acid. Okay, we have CHO. If it gets oxidized, one more what to say, basically this is one more oxygen gets added up, so this becomes COOH. Okay, so if this gets reduced, it results in the formation of alcohol. Okay, so an aldehyde on oxidation gives you acid, on reduction gives you alcohol. This is simple, that you have, when the functional group of alcohol is OH. Okay, so this is something which you would have known from your schools. So this is it. And so now let's see what happens to glucose. So in glucose, if it gets oxidized, so what should it give you? It should give you an acid, right? So if C1 of glucose gets oxidized, then we get gluconic acid. Okay. Similarly, if C6 of glucose gets oxidized, we get something called as glucuronic acid. Okay. On the other hand, if both C1 and C6 gets oxidized, we get something called as glucosaccaric acid. Okay, so this is about oxidation. So glucose gets oxidized. So whenever glucose gets oxidized, we get an acid. And if C1 of glucose gets oxidized, we get gluconic acid. If C6 gets oxidized, we get glucuronic acid. If both C1 and C6 gets oxidized, we get glucosaccaric acid. Right? This is also called as a dicarboxylic acid. Okay, dicarboxylic acid. Similarly, in galactose, if C1 and C6 gets oxidized, it's called as galactosaccaric acid. So this galactosaccaric acid has a special name called as music acid. So music acid test is a test which is done to detect presence of galactose. Okay, this is it. So now let's see what will happen if it gets reduced. So glucose, if it gets reduced, it should form an alcohol, right? Yeah. So glucose on getting reduced forms what is called as sorbitol. Okay. Galactose, if it gets reduced, it will form something called as dulcitol or galactitol. Okay. Similarly, mannose gets reduced to form mannitol. Okay, fructose gets reduced to form both sorbitol plus mannitol. Okay, so this is something you'll have to know. Glucose gets reduced to form sorbitol, galactose gets reduced to form dulcitol, which is otherwise called as galactitol, mannose gets reduced to form mannitol, and fructose gets reduced to form sorbitol plus mannitol. Fine, so this is it. So now with these concepts, let's move on to the most interesting topic, which is isomerism. So under isomerism, we have two major topics to discuss. One is structural isomerism or stereoisomerism. So this structural isomerism is divided into four. One is D and L isomerism. Remember, it's capital D and capital L isomerism. And then we have something called as anomerism. Okay, anomerism. And then we have something called epimerism and diastereoisomerism. Okay, and then optical isomerism. So optical isomerism is nothing but the ability of a molecule to rotate the plane polarized light. Okay, plane polarized light, depending upon how it rotates it, it is categorized. Okay, so this is it. So now let's look at structural or stereoisomerism. Okay, so as the name says, it is structural or stereoisomerism, means it has the same molecular formula. Okay, so okay, let's discuss about structural or stereoisomerism. So in structural or stereoisomerism, what it essentially means is that if two molecules, okay, there is a molecule A and a molecule B, they are said to be structural isomers if they have the same molecular formula. Okay, so molecular formula is same, okay, but structurally they are different. Structurally they are different. Okay, this is same but this is different. So this is essentially the definition of structural or stereoisomerism. So before moving on any further to the types and other things, there is something called property of chiral carbon. So what do you mean by a chiral carbon? So a carbon has four valencies, right? So 1, 2, 3 and 4. It has four valencies. It has a valency of 4. So if each of the valency of carbon is satisfied by four different, I mean, if here we have group A attached, here we have group B attached, here we have group C attached, and here we have group D attached to this carbon. So this is a chiral carbon. On the other hand, if carbon is surrounded by compound A on both sides. Okay, here it might be B and here it might be C. So is this a chiral carbon? No, because we have two similar molecules getting attached to the carbon. So this is not a chiral carbon, whereas this is a chiral carbon. Okay, so now having understood this property of chirality, now let us look at the structure of glucose. Where was it? Okay, so this is a glucose. So amongst the 6 carbons that you see, how many carbons of glucose is chiral? So we can see that there are 6 molecules of carbon, I mean carbons attached here. How many are chiral carbons? So we can see this one is not a chiral carbon. C1 is not a chiral carbon because 2 oxygen atoms are attached here. So this is not a chiral carbon. What about C2? It is a chiral carbon. Okay, C2 is a chiral carbon. C3 is also a chiral carbon. C4 is also a chiral carbon. C5 is also a chiral carbon. C6 is not a chiral carbon. So how many we have? 1, 2, 3, 4. Okay, so in straight chain we have 4 chiral carbons for glucose, whereas in the ring form it has 5 chiral carbons. Okay, because the C1 is also involved in a ring formation. It is involved in a bond. C5 is also C1 is also a chiral carbon there. Fine. So in linear form, glucose has 4 chiral carbons, and in ring form, glucose has 5 chiral carbons. Fine. So there is, to determine the number of isomers that a molecule can have, we have something called Lieber-Van-Hoff rule. Okay, which gives the number of chiral carbons, which gives the number of isomers for a molecule from the chiral carbons, number of chiral carbons, and the formula is 2 power n, where n is nothing but the number of chiral carbons. So for glucose in straight chain or in Fischer's configuration, how many chiral carbons did it have? It had 4 chiral carbons. So the number of isomers would be 2 power 4, which is equal to 2 basically 2 power 4 is 2 into 2 into 2 into 2. So 2 2s are 4, 4 2s are 8, 8 2s are 16. So 16. Okay. So for glucose in ring form, what were the number of chiral carbons? It was 5. So 2 power 5. So 2 power 5 means again 2 into 2 into 2 into 2 into 2. So we will get 32. Okay, so these are the number of isomers that are available for glucose in straight chain and in ring form. Understood? Okay, so now let's move on to each of these. So D and L isomers. So this is like a mirror image. Okay, basically a molecule and its mirror image. So these are nothing but the D and L isomers. To talk about it in detail, let's draw a structure of glucose. Okay. So yeah. So we have glucose. Let's draw glucose. C double bond O and H. Okay, and then we have CHOH, COH, H, CHOH, and CHOH, finally CH2OH. Okay, and then let me draw a mirror image on this side. Okay, C double bond OH, okay, and then COH, H, CHOH, COH, H, COH, H, CH2OH, right? So these both are like exact mirror images. Okay, what was on the left now is on the right, right? So now, with regard to the penultimate carbon atom, okay, this one is the last carbon atom, the carbon atom which is the last but the least. Okay, so that one is called as the penultimate carbon atom. If the with reference to the penultimate carbon atom, we'll have to see where the OH group is. If OH group is on the right side, then it is called as D isomer. Okay, on the other hand, if OH group is on the left side, it is called as L isomer. Okay, so this is about your D and L isomers. Okay, this is about your D and L isomers. Now, what was the next isomer? Yeah, next is anomerism. So anomerism is nothing but a similar thing with reference to your H and OH. There is some epimerism, some isomerism that is happening, but that is what is it, defined with regard to the ring structure. Okay, so now let me draw the ring structure for glucose. So it looks something like this, right? C1, C2, C3, C4, C5, and C6. So in C1, there should be H here and OH here, right? If this is the orientation of H and OH, so OH is down. If OH is down, it is called as alpha glucopyranose. Okay, on the other hand, if it's on the other side, if say OH was here and H was here, if OH was above, then it is called as beta glucopyranose. Okay, so this is something you should remember, and this beta form, beta glucopyranose, is the most commonest existing forms. Fine, so this is about this thing, and just remember this concept here. This alpha glucose, how it rotates, there is some property of this anomeric carbon to rotate the plane polarized side. So this alpha carbon, alpha glucose, glucopyranose, rotates it by plus 112 degree, and beta glucose rotates it by plus 19 degree. Okay, and in equilibrium, so what do you mean by equilibrium? In equilibrium, which means alpha is equal to beta. When alpha glucose is equal to beta glucose, this rotation is plus 52.5 degree. Okay, so at equilibrium, when alpha glucopyranose is equal to beta glucopyranose, the rotation is plus 52.5 degree, and this is called as mutarotation. Okay, okay, and sometimes there is a concept called racemic mixture. Okay, so a racemic mixture is nothing but the proportion of alpha and beta that has to be put in so that the net rotation is 0. Okay, so mixture of alpha and beta in such a proportion that the net rotation is going to be 0. So that's nothing but your racemic mixture. So just remember, anomerism is nothing but with regard to the ring structure, the orientation of H and OH. If OH is above, it is beta glucopyranose, and if it is below, it is alpha glucopyranose. Beta glucopyranose is the most commonest existing form, and then because of this anomeric carbon, the property, it facilitates the rotation of plane polarized light, and this alpha glucose always rotates it by plus 112 degrees, and beta glucose rotates it by plus 19. And in equilibrium, when the concentration of alpha and beta glucose is equal, it rotates it by 52.5 degree. So this is called as mutarotation. And next thing is this property of rotating plane polarized light is called as mutarotation. Okay, and then racemic mixture is nothing but the proportion of alpha and beta that has to be put in a mixture such that the net rotation is 0. Okay, that's nothing but your racemic mixture. So this is in short about Anomerism, and then we have Epimerism. So Epimerism is the difference in structural orientation with regard to only one carbon atom. Okay, so initially when we discussed D and L isomers, the capital D and capital L isomers, so here it was like the D isomer and the L isomers are like complete mirror images of each other. But here in Epimerism, the difference in H and OH is with regard to only one carbon atom and not in entirety. Fine. So that is about yeah. So that is about epimerism. So epimerism is difference in orientation of H and OH with regard to one carbon, and that carbon shouldn't be your reference carbon or penultimate carbon. Okay. Basically it shouldn't be your penultimate carbon or it shouldn't be your functional group. So if the difference in H and OH, if there is a difference in the orientation of H and OH between two molecules, and that difference should not be in the reference carbon or the penultimate carbon or nor the functional group. Okay, so let me draw glucose again. C double bond O and H, and then we have CHOH, and then we have COH, then we have CHOH, then we have CH, then we have CHOH, then we have CH2OH, right? So this is nothing but glucose. So this is our functional group. So functional group, there is so I told you functional group is an exception and the penultimate carbon is also an exception. So this is the ultimate carbon, so this is the penultimate carbon, right? So this is the penultimate carbon. So excepting this, there are three other carbons, right? C2, C3 and C4. So how many epimers are possible for glucose? 3 epimers are possible for glucose, right? So let's discuss what are these. Okay, so now let me draw the C2 epimer of glucose. This is glucose. The C2 epimer will look something like this, right? CH double bond O. C, so difference in H and OH. So OH has to come here, H has to come here. This is C2. C3 has to remain the same. OH, H. C4 also has to remain the same. H and OH. And C5, no changing. H and then CH2OH. So C2 alone is differing from glucose, right? The H and OH, the orientation of H and OH is differing okay, in C2 alone. So what is this? This is nothing but the C2 epimer of glucose. C2 epimer of glucose is mannose. Okay, so remember mannose has two ends in it. So it is, since it has two ends in it, I remember it is the C2 epimer of glucose. Fine. Okay, so now let me draw C3 epimer of glucose. So C3 epimer of glucose will look like this. Okay, C3 will have, C2 will have the same orientation. C3 will have H here and OH here. So what is this? C3 only with regard to the third carbon, C3, there is a difference in H and OH with in comparison with glucose. So this is nothing but C3 epimer. So C3 epimer of glucose is called as allose. Okay, C3 epimer is called as allose. Now let me draw C4 epimer. So how will C4 epimer look like? Yeah, so C4 epimer means this thing should be yeah, OH here and H here, and this thing should be OH here and H here, right? Yeah, so now C4 alone differs from that of glucose. So what is this called? C4 epimer of glucose is called as galactose. Okay, so I hope you remember when we discussed lactose, I told you lactose is made up of galactose plus glucose, and galactose is a C4 epimer of glucose. So this is what is the epimers. Okay, so epimer, now let's go back to the definition. What is an epimer? So an epimer is nothing but difference in with regard to the orientation of H and OH, but with respect to one carbon, which should neither be the reference carbon or the penultimate carbon or the functional carbon. Fine. Okay, so now let's move on to, okay, so now that we have discussed all three epimers of glucose, how is mannose and galactose related? So this is, I'll draw mannose. This is CHO, and then mannose is C2 epimer. So this should be OH, and this should be H, and then the other C's are, this should be OH and H, this should be H and OH, and this should be H and OH, and this is CH2OH. So this is your mannose, right? So now let me draw galactose. So galactose is C4 epimer, right? C4 epimer. So CHOH, COH, CHOH, CHOH, COH, CH2OH. So this is your galactose. So how do these both differ from each other? So in between these two, we can see that with regard to C2, there is a difference in H and OH orientation, and with regard to C4, sorry, this is C5, this is C3, C4. With regard to C4, there is, this is C3 and this is C4. There is one more difference, right? So this here we can see that there is a difference in orientation of H and OH with regard to C2 and C4. So because there is difference in two carbons, this is called as a diastereoisomer. Okay, so this is called as diastereoisomerism. Okay, if the difference is pertaining to two carbons, it's called as diastereoisomers. Fine. So now we are done with how many? We are done with DNL, we are done with Anomerism, we are done with Epimerism and Diastereoisomerism. The last but the least, we have optical isomerism. I told you already, it is the ability to rotate plane polarized light. Okay, again, it's a property of your anomeric carbon, and if it rotates to the right, it is called as dextrorotatory. Here, remember, it is now denoted by the small d here, or you can also use the symbol plus. Okay, if it is rotate, if the plane polarized light rotates towards the right, it is called as dextrorotatory, denoted by small d or plus. If the plane polarized light rotates to the left, we call it levorotatory. Here we use the term small l or minus. Okay, so this is it. So now we have come to the end of isomerism. So now shall we just summarize? Okay, so we began with what carbohydrates are. So carbohydrates are essentially aldehyde or keto derivatives of polyhydroxy alcohols. So it is, I give you an example from like how glyceraldehyde and dihydroxyacetone are derived from glycerol. Glyceraldehyde being the aldo derivative and dihydroxyacetone being the keto derivative. And then we saw the different classifications of carbohydrates, monosaccharides, disaccharides, and so on. And monosaccharides were further classified depending upon the number of sugars that were present. The commonest one is hexose here. So the aldo hexose is glucose, commonest one, and a keto hexose is fructose. Okay, and then we also went on to disaccharides. So disaccharides were divided into reducing and non-reducing. Under reducing, we discussed maltose, isomaltose, lactose, and lactulose. Maltose is glucose plus glucose in alpha 1,4 linkage. Isomaltose is glucose plus glucose in alpha 1,6 linkage. Lactose is galactose plus glucose in the beta 1,4 linkage. And then lactulose is galactose plus fructose. And then non-reducing sugars, under non-reducing sugars we saw sucrose and trehalose. Sucrose is a combination of glucose plus fructose in alpha 1 beta 2 linkage. Trehalose is glucose plus glucose in alpha 1,1 linkage. Fine. And then we also saw the ring structure of glucose and fructose. So glucose exists in a pyranose ring, fructose exists in a furanose ring. So glucose pyranose ring is 6-membered, whereas fructose furanose ring is 5-membered. And then we looked at oxidation and reduction of glucose. So glucose, when it gets oxidized, if C1 gets oxidized, we get gluconic acid. If C6 gets oxidized, we get glucuronic acid. If both C1 and C6 gets oxidized, we get glucosaccharic acid. On reduction, if glucose gets oxidized, we get sorbitol. If galactose gets oxidized, we get dalcitol or galactitol. If mannose gets oxidized, is reduced, we get mannose, mannitol. If fructose gets reduced, we get sorbitol plus mannitol. Fine. And is it now? Then we moved on to isomerism. So under isomerism we talked about structural and stereoisomerism, under which we discussed about the capital D capital L isomerism, anomerism, epimerism, and diastereoisomerism, and optical isomerism. Okay, optical isomerism is a separate phenomenon. It's not under structural or stereoisomerism. Fine. So this is it. So if you have any doubts, you can comment. And this is it. I hope you understood. Keep revising. All the best.